Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at some new activities, STEM on the fly. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI Technology to make tough-to-teach, tough-to-learn activities for all my students. I'm very excited to be joined by our two panelists tonight, Curtis Brown and Eric Archer. Curtis is the market segment manager for the mathematics education market with Texas Instruments. Currently, he is heading up the development of content-based math programs such as building concepts and activities in STEM Behind series. Curtis was an AP Statistics and Algebra 2 teacher in Houston and worked as a statistics content specialist at the National Math and Science Initiative. Curtis, thanks for being with us tonight.
You bet. I'm excited to be here.
And Eric is the market segment manager for Texas Instruments. He continues to lead the efforts for the development of content-based STEM programs, such as STEM Behind Hollywood and STEM Behind Health. Eric, so great to have you with us tonight.
Thanks, Mike. I'm glad to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Curtis or Eric using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance, as well as a link for the documents that are being used tonight at the conclusion of the webinar. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Eric is going to discuss our agenda.
Thanks, Mike. Yeah, so we've been through the welcome and the introductions. Tonight we're going to talk about STEM Behind Cool Careers, and specifically one activity from that program. That program we launched about a little over a year ago, and the activity tonight was the last activity in the STEM Behind Cool Careers program. And we're also going to talk about, conceptually, we'll talk through the flight, the math and the science behind how an airplane works. We'll talk a little bit about Bernoulli's principle, Newton's third law of motion, some of the ratios involved in required to achieve lift, and some other things that I think you'll find interesting.
Thanks so much, Eric. Curtis, I'm giving you control. Feel free to share your screen.
You better watch out. You gave me control. All right. So, so we're going to check out this STEM Behind Cool Careers, and I'm going to navigate. So we've landed on the education.ti.com website, and I wanted to just make sure that we showed you how to navigate through the website to get to the activity we're going to be talking about tonight, so you can find it. So underneath the Activities tab on the website, you'll find STEM Activities, and if you click on that, you'll be led to a large collection of activities related and involving STEM. And this particular activity is part of, like Eric said, the STEM Behind Cool Careers activity. So we'll go in and click on this tab here. It says Explore the Activities and check out a few things. Eric, you had a few comments probably about this project.
Yeah. Oh, sure. Yeah, thanks, Curtis. So just to remind everybody, all of the STEM Behind activities, STEM Behind Hollywood, STEM Behind Health, STEM Behind Sports, and so on, they are all either or both math and science activities. So some of these cover both math and science, like the one that Curtis and I are going to talk about tonight. Some of them are really more science, some of them are really more math, but they all involve some kind of STEM career. And so even in STEM Behind Hollywood, in the zombie activity, which most people are familiar with, that one talked about epidemiology, being an epidemiologist and what that entailed. Tonight, our activity is going to talk about aviation as a career. And in fact, we'll get into it a little bit more here, but Curtis, if you could, thank you. Yeah, scrolling. Curtis is scrolling on the page to show you that there are 4 activities in the STEM Behind Cool Careers program. There's Ice Cream Cool Science, STEM or Style by STEM, and there is Math and Art Form, and then of course the one we're going to do tonight is STEM on the Fly. All 4 of these activities can be used with either the TI-84 plus CE or the TI-Nspire CX handheld. They have a lot of images in them. They're kind of like an e-reader style where you go from page to page. Yes, even on the 84 CE, and Curtis is going to show you some of that here in a minute. The Ice Cream Cool Science activity gets into the states of matter and changes in the states of matter when making ice cream. And a cool little tidbit, when you eat a scoop of ice cream, you're actually consuming all 3 states of matter at once, solid, liquid, and a gas. So I'll let you bake on that for a minute and think about that. But if you want to find out what I mean by that, it's best to check out the activity. The Style by STEM is a really cool activity that gets into fashion design. So the whole point of STEM Behind Cool Careers was to help teachers, help students see that math and science are present in just about every career possible. And so we try to find some careers that students may not think about as STEM careers. So the ice cream activity is really about food science. The Style by STEM is fashion design and all the mathematics required to be successful in that industry, to be a successful designer. And in fact, in that activity, your students are challenged to make a circle skirt using geometry. So that's pretty cool. And then, Curtis, can you scroll a little bit more on that page? And then Math and Art Form, this one's a treat. This one is getting into scale and proportion ratios. The kids have to actually repair a mural that's been damaged on a wall, and they do that virtually, and it's pretty slick. But they have to understand the math in order to do that. Now, all of these activities were done with the help of an expert in their field. So the ice cream activity was done with a local ice cream shop, Beth Marie's Old Fashioned Ice Cream in Denton, Texas. Actually, they're starting to distribute now because it's so good. And then Math and Art Form was done with a couple of muralists here in the Dallas area that have done some amazing work, beautiful murals around town. The fashion design activity was done with the help of a couple of fashion designers in the Dallas area. And then finally, the one we're doing tonight, STEM on the Fly, this one came about from the contest. There was a STEM Behind Cool Careers contest, and the student who won the contest, you can see him here in the image, his name is Alex, and Alex wants to be a pilot when he's old enough. And so Alex wanted us to do an activity on aviation. Now, although aviation is a little closer to what some people would think about as STEM, we went ahead and did it anyway just because this kid was just so impressive. So I encourage you to go to our website, check out that video. The gentleman next to Alex is a Southwest Airlines check airman named Adam Schindel. And a check airman is basically a person who trains other pilots. This guy's got just thousands and thousands of flight hours under his belt, and so he's pretty much Southwest, one of their best pilots. And so he works with new pilots in the simulators, and he grades them, and he helps them, and he trains them. So this guy really knows what he's talking about. And so Adam and Alex helped Curtis and I develop this activity, and we hope you guys like it. All right. Curtis, did I miss anything there?
No, I don't think so. Just the fact that we learned an incredible amount from these two guys, and it was a whole lot of fun working with them on this project. So, yeah, it was eye-opening. We took a tour of Southwest Airlines. We saw their simulators. We got Alex behind in the cockpit of an actual airplane. He didn't fly it, but he used one of Southwest's simulators that they train pilots with. He was in there for a couple of hours working with Adam, and just had a blast. And so I think this kid's definitely going to end up being a pilot. He's just so passionate about it.
Yeah,
okay,
for sure.
So here we are. Go ahead, Curtis. I said, yeah, for sure.
Yeah, I mean, he's a neat kid. So Curtis has the TI-Nspire CX software pulled up, and the first page is a title page, STEM on the Fly. And Curtis is going to be flipping back and forth between the 84 CE version of this activity and the Nspire version of it, just to show everyone on the phone that you can do it with either handheld platform. So that's a real nice piece. And then if we have time a little bit later, we're going to look and see how we're going to let you guys know how to get this program on your TI-84 CEs because you have to download the program file and the associated images. Okay. All right, Curtis, you want to go to the next page?
Sure.
Okay. All right. So like all of our activities in the STEM Behind Cool Careers, STEM Behind Hollywood, STEM Behind Health activities, we tell a story. We try to tell a story so kids have something to relate to, so we try to make it a little more real world for them when these activities are developed. So we start off by letting kids know that typical airliners got the mass of about 70,000 kilograms, which is insane. And so when we talk about weight, in science class, when we talk about weight, we're not really talking pounds, we're talking newtons instead. And so weight is a force, Newton is a measure of force, and so that means that the plane's weight is about 700,000 newtons. So that's a lot of mass to get up into the sky, and we need a force to do that, and that force is called lift. Okay, Curtis? All right, so in addition to lift, there are other forces that act on an airplane, and a lot of you are already familiar with this most likely, but a lot of kids aren't. So we get into a little bit of the vocabulary here, and the next page, I think, is a better illustration of these definitions, is a little more interactive way to deal with vocabulary. So here's an image, and you'll notice Curtis's cursor is moving around the screen, and when he goes to one of these definitions, these terms, the definition will pop up. And so lift is a force that acts at a right angle to the direction of motion through the air. Lift is created by differences in air pressure. And so kids probably don't know what that really means. And so throughout the activity, we try to slowly build these concepts up through experiences that they'll have. Curtis, jump over to thrust real fast here.
Sure.
So thrust is the force that propels a flying machine in the direction of motion. Engines produce thrust. So we looked at two forces so far, lift and thrust. And with lift, the way we control lift is with the wings. And we have to change the surface area of the wing to achieve lift and based on the speed of the airplane. And now the speed of the airplane is achieved through thrust, and the engines are able to generate that velocity for us. We're going to talk a little bit about Newton's third law of motion here in this activity, as well as Bernoulli's principle. But before we do that, let's look at the other two forces that act on an airplane. So drag basically is differences in air pressure and friction. It's air resistance, essentially. And so as the plane moves faster forward, there's going to be more drag associated with it. And so you have to have more thrust than you do drag to keep the plane moving in the right direction. And then the last force we'll talk a little bit about is weight. And weight is the result of gravity and the mass of the airplane. And so it acts in a downward direction, which is opposite of lift. Toward the center of the earth, of course. All right, so those are the four forces that act on the plane. Two of those forces we can really do something with, lift and thrust. We can control those for the most part. Drag and weight are a little more difficult to influence. You can decrease drag by making the plane more aerodynamic, which is why planes don't look like buildings flying through the sky. And then weight. Weight is something that's really controlled by gravity, so not a whole lot we can do about that. So the two forces we can control, we try to do as efficient a job as possible. All right, Curtis, we'll jump over to the page 1.5.
I was going to just really quickly navigate to 84, just show the navigation is kind of similar. So on Nspire, you're using control in the arrows. On 84, you're just going to be using the right and left arrows to get things going. But you'll notice the page numbers are the same, and the interaction is very similar to the way that it was on the Nspire. So there's instructions for 84 just like there are for Nspire. So I'll navigate to that page for you here, Eric. Just wanted to make sure that we're all comfortable here, that we're doing the same thing on both platforms.
Obviously the graphics look a little bit better on Nspire, but I think we did a good job of trying to make sure the experience was as close as possible on the 84 CE as the Nspire. I think it's really fun going to math and science conferences and showing people what you can do with the 84 CE other than making calculations and graphing. You can actually tell a story right on the handheld using this format. So in this particular activity, the 84 CE is really like an interactive e-reader in a way, but it's also a calculator, because Curtis will show you in a few minutes that this activity requires the kids to do some computation to try to get closer to the best possible answer to achieve lift on a virtual airplane. All right, so we talked a little bit about the four forces that act on an airplane. This page just goes into some more background information specific to lift. So the wing surface area, the air temperature, air density, humidity, these are factors that will affect lift. And there's some kind of ahas that we'll get into a little bit later with one of the simulations that Curtis is going to talk through when it comes to air density. Air density can be a real bummer when it comes to aviation. So I'll leave it at that. Curtis, I'll let you tell them more about that.
For sure. We'll address that real quick. Eric, I want to show folks really fast the teacher document, and you referred to that we actually did put in some nice information here on Bernoulli's principle and some of the science concepps in here. And I know we put in a big caution here, and I thought maybe before we jumped into the math portion, let's hit this real quick.
Yeah, absolutely. In addition to Bernoulli's principle, which we haven't talked about too much yet, Newton's third law also has a role in lift and achieving lift because the way the plane's wings are angled and in which they're taken off, there's a process called a downwash. And so as the air hits the bottom surface of the wing, it's redirected, which causes a equal but opposite reaction on the wing, pushing it up, causing lift. And then the image that Curtis is showing right now is an image of Bernoulli's principle, showing that the motion of the air across the top of the wing is different than the motion of air below the wing. Now, what happens here, Bernoulli's principle states that as air velocity increases, air pressure decreases. And so the faster the air is moving across the top of the wing, it creates a lower pressure environment relative to below the wing, which is higher pressure. So it's the plane's literally being lifted away from the surface of the earth because of it's kind of a vacuum effect almost because of the air pressure differences. Now, Curtis, do you mind scrolling down real quick to the little the red text here? So you'll notice a misconception alert. Man, we did a lot of homework on this. We spoke to a lot of people, and one misconception that you'll notice if you look at Bernoulli's principle diagrams online, or if you're looking at like maybe some older simulations, there's an idea called the equal transit theory, which basically says that two air molecules that are parallel, one above, one on top, or one below, as they travel, one on top of the wing and one below the wing, that it is true that the air molecule above the wing is going to have to travel faster than the air molecule below the wing because of the surface of the wing. The surface area is higher on the top portion of the wing. However, what's not true is that those air molecules will end up at the same place on the back side of the wing. It turns out that that's not the case. So this equal transit theory has been shown to be incorrect. However, I will say that Bernoulli's principle still holds true here, that the air molecules above the wing are traveling faster than air molecules below the wing. It's just that they don't end up at the same place at the same time on the back side of the wing. Okay? All right.
Yep.
Yeah. It's a small kind of distinction, but we have found out through trial and error that it can upset some people if we didn't address it. So we wanted to make sure we addressed it and made you all aware of it, because when I was in school, I was taught that the equal transit theory is true, and that Bernoulli's principle operated that way. Not quite the case. Okay.
Right.
All right.
Right.
So in this document, Curtis has shown you, these are images in the teacher document. These are also present in the student document. The images you're seeing right now, just real quick, James Pickard just put a question. He said it's a bit too deep of a concept for high school kids. Yeah, you're totally right. We put that in there just to let folks know that, hey, just a heads up, this is a thing. Just be careful with it. I don't think you need to get into it too much with the kids. I think you just need to let them know, the basic concepts of Bernoulli's principle. But totally agree with you. We just put that in there just so you're aware of it. Now, the image that Curtis is showing you just shows three different types of airplanes. So we have a glider, a jet, a prop plane. And the glider, you'll notice the wings are long and narrow. The glider doesn't have any thrust of its own. It has to get thrust from being towed by another airplane and or gravity from falling. The jet has smaller, more compact swept-back wings with two jet motors. And then the prop plane, all the thrust is coming from that propeller in the front part of the plane. The wings are more rectangular, very wide, a little shorter than the glider. So all three of these airplane types are designed the way they're designed because of the different types of thrust for each one of them. If you have more thrust, your wings don't need to be as long, it turns out. If you have less thrust, you need bigger wings. A glider has long, narrow wings because long, narrow wings give you the lift you need without the drag that wider wings may cause. Okay. All right.
Yeah, I think that's good, Eric. Thanks for kind of tackling that. So really from here, the lesson kind of stretches, and we begin tackling some more mathematical concepts. And so the next kind of step in this lesson, we've introduced the concept of Bernoulli's principle and explained that lift kind of comes from a combination of different things. And now we want to just kind of explore some of the variables that affect lift. Now, as Eric talked a minute ago, that we have the ability to control our thrusts pretty easily. We can, hit the gas a little bit more. And we also have the ability to control the surface area of the wings. One of the pictures in the lesson actually showed that there's some slats and some flaps that are on the front and back edges of the wing. And so in certain cases, those can be extended and retracted to change the surface area of the wing. And so that's actually what we're going to do in this next little piece here is get the kids an opportunity to just explore the relationship between surface area of the wing and its effect on lift. Now, one of the things, in fact, I'm going to just jump over to the 84 because, I don't know, I have fun working on the 84 for this particular portion of the activity. So we'll actually do a couple of things. We'll change some of the other variables at a different point here, but for now, all of the other variables, speed, air density, all those things are going to be held constant. The only things that we're going to be adjusting here, the only thing we're going to be adjusting is the surface area of the wing, and the way we're going to do that is by extending the flaps and slats. And so students are actually just asked to really quickly use the arrow keys to extend the flaps and slats. And you'll notice what I'm giving you are actually only just the lengths, how far out these are being extended. So they're not being extended very far. If you notice, that's not a whole lot of change, 20, 30 centimeters. We're not going out a tremendous amount, and that's actually pretty true to the way that these planes actually work. But students are given the dimensions of this wing and asked to compute area of the wing for each of those extensions. So what we'll do is we go through and we extend it, we compute an area, note the lift, compute another area, note the lift, compute another area, note the lift, and I'll show what that kind of looks like in the teacher document, just so that you can kind of check it out. And students go through filling out this table, computing lift and area for each of those settings, and then we ask them to check out, okay, so what is the relationship? How are lift and area changing together? So we calculate this delta lift over delta area from one piece of the table to the next. And one of the things they should notice right away after they've done maybe two of these or three is, oh my gosh, lift and area, it seems like every time I change this, we're getting the same rate of change. We're seeing this same change relative to the change in area. What's going on? That's kind of interesting. And so the prompts actually then ask the students to kind of comment on that. And so the hope is that students will go, wow, it sure seems like maybe lift and area are linearly related. These two things seem to be changing at exactly some sort of proportional relationship, or at least linear constant relationship between the two. And so then the next prompt kind of says, well, you know, one of the other pieces that can affect this is air density. And so if you'll notice, this screen didn't give you a whole lot of information just now as I was talking to you about it, but we're actually, the outside temperature is 50 degrees, if you didn't know that. It's 50 degrees right now, and we're all in San Diego, sitting here ready to take off on the tarmac in San Diego. It's 50 degrees. Actually, that's probably pretty close to what it is today. And we wanted to kind of introduce the idea that San Diego is sea level, right? So air density is going to be pretty much as high as it can be. And air temperature actually affects the air density. Of course, you know, as you increase air temperature, the density of air, the space between air molecules actually increases as you increase air temperature. So we thought, well, we could probably go someplace else to explore this other extreme. So air is pretty dense in San Diego at 50 degrees, but if we navigate, I can't navigate unless my flaps and slats are at 0. So I'm going to go a little bit further to the east from San Diego and land in Phoenix. And it just so happens that today in Phoenix, air temperature is 122 degrees Fahrenheit. It's an extremely hot day. And also, another piece of information is that the humidity has risen an amazing amount. It's just this random thing that happened. Okay, it's a bit contrived. I get that. But this event can kind of happen where you have an extremely high temperature day and an extremely humid day kind of all at the same time. And what can happen is air density drops below a point where airplanes can take off. And so this actually has happened at Phoenix. We've experienced that a couple of times where the conditions were just such that the air density was so thin for them that they are so light that they couldn't get enough lift to take these airplanes off. And so students will actually now explore the same relationship. They'll explore the same thing here, going back and saying, okay, is it linear everywhere? We've changed air density. Let's try this same exploration. And so we do this again. We note surface area. We make the same computation, coming up with some areas of parallelograms. And then we get to lift, and we make that association. And, oh, my gosh, it turns out it's, again, a linear constant relationship. We're seeing that this, as we change area, we have this proportional change in lift. And so we're seeing the same kind of constant rate of change between area and lift. And, oh, that's great. We have kind of discovered that, hey, lift and area are linearly related at least. And if we want to extend that a little bit further, you can actually work those numbers backwards. And turns out that lift and area are actually are proportional related, not just linearly related, but actually you go, which makes some sense, right? If you had a wing that had zero surface area, you probably wouldn't get a whole lot of lift out of it. Then we thought, well, hey, we have the ability to control another variable. And we can control the speed. We actually, speed on the ground is kind of hard to get going much faster than about 250 kilometers an hour on the ground. But, when you're in the air cruising, you can actually you can change the speed. Now, it wouldn't make a whole lot of sense to extend your flaps and slats while you're in the air because at those speeds, you'd probably rip them off, and they're just not that strong to be able to deal with the increase in drag, so they would rip off. So we're not going to extend the flaps and slats, but we are going to talk about how speed or velocity and lift are related. So we're going to go through the same data collection kind of process, and this time we'll extend the speed, we'll increase the speed. Notice we're increasing the speed at a really nice number, 10 kilometers an hour every click here. And what do you notice about the relationship between lift and speed? So we'll go through that again. So it increases, about 1,600 newtons there, and then, or 16,000, I guess. And then a little bit more here. Boy, that looks like it got a little bit bigger. And then it got bigger faster. And I'll show you really quick because it's not as obvious. I can't actually see it. I was pretending. So the relationship between lift and velocity, students as they go through that same sort of table exploration, they'll notice that lift to velocity, that relationship, that ratio is actually increasing in value. And so that as you're going faster, as velocity is increasing, lift is actually increasing at a greater and greater rate each time, which is, it's like, whoa, okay, so we're going faster a smaller and smaller rate each time. So we're going faster and faster and faster, man, and we're increasing lift, but we're increasing it at less and less each time. So it's not linear. It's not a linear relationship between these two. So students can recognize that. And that's all we're asking them to do is just recognize that, hey, lift and speed are actually not linear in relationships. So we have this linear relationship between lift and surface area, and as we change speed or velocity, we have a nonlinear relationship. And it's kind of a cool deal. Some students may want to kind of extend this, depending on the level of your students. You may want to go back and look at this relationship and say, okay, well, can we fit some models to this? Can we start kind of trying to figure out, okay, we know it's not linear, but what kind of relationship might it be? And this is where entering this data into a stat list and doing some regression might be of some interest. I actually would even take it a little bit further and just have students enter the data in a stat list, plot a scatter plot, but then instead of fitting data to it or fitting a regression model to it, let's actually just start fitting some functions and try to let them kind of begin to develop maybe some parent functions that could have that same similar shape. And kind of try to tackle that from sort of a transformation of some parent function that they think has that appropriate shape, and then let them explore. So there's some ideas, the ways that you could maybe extend question 16 in this lesson. Finally, as we get to the end of this, let's take it back to maybe we don't know the relationship, maybe we don't know how lift and velocity are related. Let's actually jump and look at this question number 22 in the document itself. We give the lift equation, and it's this kind of scary-looking relationship. Lift is equal to the coefficient of lift, which is just a number for the airfoil, the wing, that actually is computed on the ground in a wind tunnel. The actual shape of the wing and the design of the wing goes into that computation. So there's a coefficient of lift, and you can actually find this information. It's pretty interesting. You can go out and look at the designs of these different airplanes, and you can find coefficients for lift all over for different designs of airplanes. But they're pretty constant for the wing shape. And then rho being the air density, and then V, velocity, and the surface area of the wing are the things that we actually are going to deal with for the lift equation. And what we're going to ask students to do in this case is just ask them to look at that equation, and holding everything else constant, can you explain why lift and surface area are linearly related? Well, you know, if we take and we look at this, and we look at this section, all of these pieces then we're saying, hey, well, velocity we're going to hold constant, rho is going to be constant, coefficient for lift. So all of this can just be brought down into some coefficients, some K, some constant of proportionality, and then we see that lift and surface area are in fact just proportionally related, which means that they're linearly related. And so that's kind of an interesting, hey, we're just looking at this from kind of this, what does this equation look like? Can we make a claim about that? And then the next question is the same bit. Say, okay, but now can you explain why velocity and lift have that same sort of relationship, that they're nonlinear? Well, gosh, if we hold rho constant and the surface area constant and the coefficient for lift constant, L is related to velocity as v squared. And so we have kind of this, that lift is proportional to the square of velocity, and so that's not a linear relationship. And so students can kind of see and explain that. They don't necessarily have to know what the picture looks like. They can just explain that, hey, I noticed that we've got this squared exponent here as it relates to lift, and so these two definitely can't be proportional and certainly aren't linearly related. So just kind of a way to evaluate the relationship between those two. So once students have kind of had some fun learning about lift and surface area, lift and velocity, now it's time to kind of put that learning into action. And so what we want to tackle next is just a couple of simulations. And actually, Eric, this was kind of this is where we started this whole lesson. Was we wanted to make some variety of a flight simulator on the calculator,
yeah.
right? We got this opportunity to do a airplane program and lesson. Let's make it a flight simulator. Let's do something cool. And so we tried to do that, at least in some form or fashion, and tie it back to the things that we were going to talk about in the lesson. So, so this is what we're going to do next. We're going to check out how this airliner can get off the ground, because we have a mass of 70,000 kilograms, and we saw that we can generate lift of more than 700,000 newtons, but there's some kind of skill and strategy to adjusting the velocity and wing area to optimize the lift for takeoff. And so we didn't really give students any background saying, hey, you want to be as close to 70,000 newtons as possible, but maybe just slightly more. But that's kind of the goal here. And then students have a couple of variables they can play with. And so we'll do that. I'll give you a quick demonstration of messing with velocity and surface area to try to optimize the lift. And so I'll give you kind of a couple of just the way that it works. Of course, the graphics look a little bit better on Nspire. So I'll do one version of it here on Nspire, and you can see how I didn't get the lift high enough because I wasn't above the 700,000 newtons. So I might go back in, and I could retry that. I might get a new piece. But I want to show you just kind of what it looks like on the 84 here. And you'll notice every one of these 84 pages, I want to give you one more kind of tip on this, using this with your students. We put in here kind of how you navigate. So the left and right arrows are how you navigate left and right through the lesson itself. But anytime that there's a page that is sort of interactive, that there's some kind of a simulation that we want the students to do, we've actually changed the border around the screen. And so you'll notice that if it's a kind of a notes page, it's a green border. Blue page is a simulation. And then pressing enter is how you're going to enter into any of these simulations. And then we give you kind of how you're going to use arrows or the plus and minus keys to do some different things. And then clear is always going to be your exit from those simulations on the 84. So just some navigational tips here. But I want to let's look and see what it looks like here. So we have a menu option instead of the sliders like you have the clickers on the Nspire. But it's the same thing. You're using the left and right arrows to set your velocity. And I'll just do this really quick so you can see that we don't have an airplane taking off. We have a ball taking off on 84, but it looks still pretty neat. Just there's motion on screen on the 84. I got in the air that time, but I had a little bit too much lift, so I could optimize that, and we could certainly play with that just a little bit more. And then finally, students, go for it.
Oh yeah, sorry. I just real quick, just reiterate some of the things the points that you're getting across here. So the airplane weighs, we said it weighs about 700,000 newtons. That was its weight. And your lift is just above the weight. So we have a forces that are in opposite directions. We have lift moving up, and then we have weight moving down. And so we need the lift to just get past the weight. And that's how you see, perfect. All right, so great combo of velocity and surface area. And what you saw Curtis do earlier on the 84 screen is he had just too much lift. He's too much. And so you saw the airplane take off pretty dramatically. That would be definitely a rupture your eardrum kind of takeoff that he showed you earlier. And then I just want to say one more thing real quick, Curtis. So one thing I love about this activity is that a lot of your students have never been on an airplane before. In fact, I'd be willing to say probably most of them. They see these things flying through the sky. They don't have the same experience of being in one that maybe a lot of us have had. And so for the most part, they're mystical and magical and don't really know quite how they work. And so I love this activity because it breaks down the math, it breaks down the science. I think there's some flexibility in the activity as well, so you don't have to get too deep into it. You can kind of cut out some stuff and still get the point across about the relationships between the four forces of flight, and you can leave it right there if you want. Or if you want to get into some of the linear and nonlinear relationships and go a little deeper, you can do that as well. It's possible to delete some of these pages, especially on the Nspire side, to leave some of the stuff out. So we tried to make this activity in a way that explains the mechanism of flight. And again, I think for the kids, especially the kids that have never been on a plane before and they just see these things flying through the sky, I think it's kind of cool for them to be able to have an experience in aviation to navigate something like this using math and science. So I just wanted to jump in there, Curtis, and say those things because it's really cool. And the fact that you need just a little more lift than you do weight to get that huge amount of mass up in the air is just amazing. It's remarkable.
I think it's just remarkable flat out that you can generate enough lift to get those things up in the air. And I think, you're hitting it spot on, that there's these forces that we don't necessarily think about. And initially it kind of we think, well, gosh, let's go as fast as we possibly can, or let's make that area as big as we possibly can. And that isn't exactly how you want to do it. You want to get just enough lift to break gravity, to break the weight pulling down, and so you can counteract that and get up into the air, but at a comfortable rate.
Right.
So I think that actually is that's kind of a cool key point of this activity. That we've learned some interesting things about noting, hey, there's this proportional relationship between lift and surface area. There's this nonlinear relationship between lift and velocity, but as another piece to that, it's just how does all of this kind of fit together to make flight happen. Finally, in the lesson itself, there's a cruising challenge. We won't demo it, but it's the exact same scenario. Students set a velocity, and then they actually make they try to fly the airplane and keep it in the air based upon that same sort of concept. You want to get it just above or right at the 700,000 newtons, which that's still mind-boggling to me, thinking about how large that particular number just happens to be for flying an airplane. It's just crazy. So I guess we saved just about 3 or 5 minutes here to go back and talk a little bit about how you can get these lessons onto your devices. And so back on the website, we actually have posted on the website, along with that video that we talked about, we posted on the website, several different ways that you can download the pieces and parts for this activity. Honestly, I would just download all files. Go ahead and grab that zip file. That's the fastest thing. But if you're, looking to get just the 84 or just the Nspire files, it's all posted here on the website. You'll note that the student and teacher documents are in PDF form, so it should be viewable on just about any computer platform. But if you pull the zip file for the 84, I just wanted to show you really quickly the things Eric mentioned earlier, that there's a number of files that you get when you get that zip file. So I've got the zip file open here, and I've done the extraction. And you'll notice you have the student and teacher document and then the calculator files. And so what Eric was talking about earlier was that on the TI-84 plus CE, there's about 10 image slots. Images 1 through 5 are kind of the standard ones that are loaded on there from the very beginning when you upload your operating system, which you could overwrite those, but this particular activity only uses 5 images and then 2 pick bars. And so these files, all of them, including the .8xp file, need to be transferred over to your graphing calculator. So what I'm going to do really quickly, I'm going to use my SmartView emulator. And actually, if you are putting it onto handhelds, it's kind of the same experience. It looks a little bit different. I've actually got my TI Connect here loaded up, but I don't have a handheld at home. That's why I'm going to do SmartView. So you would see kind of the same piece here, kind of a calculator explorer. In this case, it's the emulator explorer view. And you can take all those files and drag and drop them onto the device. And so there's just real quick, you'll see that it says copy, and when you let your mouse up, you'll get this dialog box, and I always go ahead and say replace everything, because I'm doing this because I want it there, not because I want to be careful about whether something else was there with the same name. So, and then I'm gonna load all of these on there. It takes a little bit of time for the picture files to go over, and the emulator takes a little bit longer than it does on the handheld. It's actually a little bit faster when you're sending it across to the handheld. But then as soon as that refreshes, we'll be able to go back to, in fact, I'm just going to go ahead and go over here. I just say change workspace, and it'll cancel my file transfers, and I'll go over, and I'll show you what it looks like here on the calculator. There's a program called STEM on the fly, so you just press the program key, third row, third column, and execute that program, and it will call up the picture variables, which are being called up in the background, and the pick bars that you need for all the different simulations and things. So that's actually the way that gets onto the 84. And I think I also wanted to show one other thing. We actually, in case I did that kind of quickly and wasn't as clear as maybe I should have been, we've actually posted a series of TI-84 Plus tutorials on our YouTube channel. So if you go out to YouTube and you search for Texas Instruments Education and check us out there, you can follow us there on YouTube. But one of the playlists that we have is a series of videos on the TI-84 Plus, so tutorials, and one of those videos is how to transfer programs onto the TI-84 Plus. So that's another quick demo and a way to get that stuff. Of course, there's a lot of other interesting information there on that portion of the website of YouTube as well, but for this particular application, transferring programs. So yeah, I think, Eric, I don't know, do you have some other wrap-up comments? But I really enjoyed building this activity and kind of thinking about how can we make an interesting but accessible lesson surrounding this really complex idea of flight and lift. And Eric, you and I spent a lot of hours chatting across the hall here, trying to get this stuff straight and come up with some good ideas. I think we came up with a pretty engaging and pretty accessible activity.
Yeah, and like we were talking about earlier, I think there's enough here to get into some pretty rich discussions and debates about mechanisms behind different aspects of flying, which if you're looking on the science teacher side, if you're looking for argumentation from evidence, you can use this activity to definitely generate some discussion for that. And then on, just in general, again, this activity is meant to both engage students in just the magic of flight, being able to take 150 people in a tin can, slap some wings and a tail on that tin can and fly them from one place to another at 500 miles per hour. It's still magical to a lot of people and a lot of kids in particular. And so this activity tries to take advantage of that wonder that most of us have about flying, but also demystify it a little bit by getting into some of the mechanisms and some of the science and some of the math to explain it. So hopefully you guys feel the same way. Again, especially on the Nspire side, this activity is very customizable. So if you have a 6th grade physical science class or a math class and you want to just keep it super simple, then probably cut out some of the nonlinear stuff. If you have a AP physics class and you want to talk a little bit about the forces of flying and the math behind it, then I think this activity is appropriate for that. So we try to make it flexible to where you can use it within a wide range of math and science classes and grade levels.
Yeah, for sure.
Oh, Curtis, there was a question about the links to the tutorials and YouTube info that you mentioned earlier.
Oh,
you want
sure.
to show that real quick?
I didn't see that question. I guess I'm not monitoring the chat.
Yep.
Okay.
Yeah, you're good.
So the link, so I've actually got this playlist here as a shortcut that could be found. But if you go to YouTube and just search our group, Texas Instruments Education, and try to go ahead and follow us, and then you'll see a list of all of our playlists that you can pull up. a list of playlists, and this particular one is the TI-84 Plus tutorials playlist. And we've got a number of videos up there on that playlist. I think close to, looks like about 19 of those videos that we just recently updated, trying to get some things ready for, just from really simple things to some more complicated mathematics kinds of pieces, and just some instruction on how to use your TI-84 Plus efficiently. So, so that, I hope that answers the question. I didn't see, still not seeing the question. Let's see if I can.
No, you're good. It was from Saba Ansari. She was just asking about if they're going to get the links and things. I was just thinking if we had a minute, you could show them our YouTube channels, Texas Instruments Education. Make sure you have the education in your search, because otherwise it will take you to the Texas Instruments main site, and in there they get into chips and signal processors and all kinds of fun, interesting things that have little to do with what you're teaching.
So make sure that you see the Texas Instruments Education group, and this little icon is a pretty good indication. This is what our current channel homepage looks like. So if you want to plop into Texas Instruments Education, that's our channel, and then you can find the playlist here underneath of this tab, and navigate to what we're looking at there. So there's a series of different playlists, and one of those at the bottom is our how-tos on the TI-84 Plus. See if I can find it. It must be on here someplace. Oh, maybe it's underneath the videos. Thought it was under playlist. I had it just a second ago. Where'd it go? I'll send that link to Mike at the end, so we can send it out to everyone. How's that? Will that work?
Yeah.
Okay. So I'll make sure that that's out there. Okay. Well, it looks like we're at 7:57 Texas time. Mike, I think that puts us pretty much to the end, huh?
It sure does. I just have a couple things to do as we wrap things up. If you do have any last-minute questions for Curtis or Eric, please try to get those asked. I know they'll try to get those last-minute questions answered. We're excited to have a new contest that started a couple weeks ago called the Extra Credit Contest. You can learn more at TI-Extracredit.com, but it's a great way to get some additional things for your classroom that you earn these entries by doing things you already do, for instance, like attending this webinar. So if you visit TI-Extracredit.com, you can find different ways that you can earn entries, and of course with more entries, you would get a better chance at winning some of these prizes. You can enter a specific code for tonight's webinar to receive extra entries, and tonight's code is Take Flight. It's not case sensitive. I'm going to type in the chat window as well. But again, that's Take Flight. Take Flight. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed as a link for the documents that Curtis and Eric used tonight. If these aren't working for you for any reason, just hang tight. You'll automatically get a follow-up email. And in that follow-up email will be a link to the recording, a link to the certificate, and a link to the documents. And if you're watching this on demand, just go ahead and copy that link into your favorite browser to receive your certificate. Thanks so much, Curtis and Eric, for everything you shared tonight. I really appreciate it. Thanks so much.
You're welcome.
Thank you, Mike.
We're excited to do it.
And thanks again to everyone for joining us. We hope you enjoyed it. We hope to see you back online real soon. Have a great night.